In this video, we will continue our investigation into power series. So recall, a power series is a series of the form given here, which is really a function of the variable x. There are two important questions that we want to explore. The first, what is the domain of this function? i.e., what are the values of x for which the series converge? And we've previously discussed how we can go about doing this. We would apply the ratio test, and that would determine most of the convergence set, and then we have to test the endpoints individually. The next important question we'd like to encounter is that if this is a function, what is the function that it converges to? So what is s of x? Recall our motivating example related to geometric series. We have seen that the sum from n equals 0 to infinity of x to the n is 1 over 1 minus x, and its convergence set is given by the absolute value of x less than 1. Now, another way to think about this is that there is nothing really special about this variable x which we are using. We can replace the x by any variable or any symbol we would like. In fact, we could think of that x as being a blank space. Whatever we plug into the blank space on the left, we need to plug into that corresponding blank space on the right, and it will converge as long as that quantity has absolute value less than 1. And moving forward, this will be a very important technique for determining power series representations. With that in mind, for the given function f of x, let's see if we can manipulate to find a power series representation. And our goal is going to be related back to the previous motivating example. The sum from n equals 0 to infinity of something to the n is 1 over 1 minus that something, and it converges as long as that something has absolute value smaller than 1. So let's see if we can rewrite f so that it has a portion in this desired form. And in order to do so, we're going to have to think about pulling the x off. That would leave us with a 1 plus x squared to take care of in the denominator. But we can put that in the form of 1 minus something. We can write this as 1 over 1 minus x squared, because minus a minus is a positive. And now specifically, the 1 over 1 minus x squared is in the desired form, and the minus x squared is the quantity that goes into the blank. So in terms of a power series, we can represent this as the sum from n equals 0 to infinity of minus x squared raised to the nth power, where that minus x squared is what we are plugging into that blank. Simplifying algebraically, this will be x times the sum from n equals 0 to infinity minus 1 to the n x squared to the n, which is x to the 2n. And algebraically, the last step would be to combine the x out front so that we have a single power series. So we would like to take the x and move it inside the summation. That would leave us inside with a minus 1 to the nth, and we increase our power of x by 1. Now the only question remaining now that we have our power series representation is to specify the radius of convergence. Two perfectly good ways to go about this problem. One would be to apply the ratio test, which turns out to be more work than we need. The second, and maybe preferred approach, would be to use the information we have below. For that radius of convergence, just take whatever we've plugged into the blank and set its absolute value less than 1. So we need the absolute value of minus x squared less than 1. That means the absolute value of x squared is less than 1, which means the absolute value of x is less than 1. So in this problem, our radius of convergence is 1. Let's begin investigating a similar example. For the given function, let's see if we can come up with a power series representation and specify the radius of convergence. So recall the basic idea is we somehow want to compare with 1 over 1 minus something. As a power series, this would be the sum from n equals 0 to infinity of that something to the n, and it converges when that something has absolute value smaller than 1. Now, because of the quantity 1 minus x squared in the denominator, it doesn't seem as though there's a direct comparison. But instead, let's make an observation. Maybe instead of making that comparison algebraically, we could make that comparison from a calculus perspective. And the perspective that I want to know is if we were to differentiate 1 over 1 minus x, this would be the derivative of 1 minus x to the minus 1. And by the chain rule, we would get minus 1 times 1 minus x to the minus 2, but then we would have to multiply by another minus because of the derivative of the inside function. So that would be 1 over 1 minus x squared. So we cannot algebraically compare with the desired formula, but we can get there through a differentiation. So we have 1 over 1 minus x quantity squared. The function we would like to represent as a power series is equal to the derivative of 1 over 1 minus x. And we know a power series representation of 1 over 1 minus x. That would be the sum from n equals 0 to infinity x to the n. So the question becomes, do we have a way or formula we can use to differentiate a power series? And it turns out that there's a very convenient formula for doing this. The following property tells us exactly what we need to differentiate and integrate a power series. So if we are starting off with a power series which has an interval of convergence, the formula we would use to differentiate it is to simply just differentiate each of the terms of the power series. That is, you can think of taking the derivative, you plug it inside the power series, and if you want to differentiate x to the n, it becomes nx to the n minus 1. When you do this derivative, plugging in n equals 0 makes it vanish, so we simply start the sum at 1. Similarly, if you would like to integrate the power series, you take that integral and you move it inside the sum. That is, you integrate each term individually. So the antiderivative of this case, t to the n, would be 1 over n plus 1 t to the n plus 1, and we would plug in that resulting x. So let's use this to answer our previous question. We wanted to find a power series representation of the function 1 over 1 minus x squared. We observed that 1 over 1 minus x squared is the derivative of 1 over 1 minus x, and we have a power series representation of 1 over 1 minus x. That would be the sum from n equals 0 to infinity of x to the n, and it converges whenever the absolute value of x is less than 1. If we would like to differentiate a power series, we simply take the derivative and we move it inside the power series. The derivative of x to the n would be nx to the n minus 1. And because this quantity inside the summation is 0 when you plug in 0, we now simply start our formula at 1. So we go from n equals 1 to infinity. And when we differentiate a power series, we do not change the radius of convergence. So it would still converge whenever the absolute value of x is smaller than 1.